Welcome to the Smart Energy System audience. I'm Elisa Guelpa from Politecnico di Torino, and with this presentation I'm glad to describe the experience that we have gained during the project Leave Second Generation Behind, which is funded by the International Energy Agency with the aim of reducing the supply temperature of the existing district heating systems. I want to take the chance to thank the other partners of the project, which are the CEA and the University of Birmingham, which I want to thank for sharing this positive experience. So the research question of the project is how to achieve supply temperature reduction in existing district heating system to allow the integration of renewable energy sources as well as waste heat, which are usually available at lower temperatures. And specifically is how to find potentials in terms of supply temperature reduction, as well as proposing ways to overcome possible bottlenecks. Main bottlenecks are due to unsuitable pipe diameter, pumping system, and thermal substations. Here, among the main achievements of the project that we obtained in the study for existing second generation district heating is in the large scale case study, it is possible to reach minus 15 Celsius degrees without any investment cost and minus 30 Celsius degrees with limited investment cost. And as concerned the small scale case study, minus 10 Celsius degrees can be achieved. There are two case studies considered in the analysis. The first is a portion of the Metz district heating, which is adopted as a small scale case study, and the Turin district heating, which is one of the largest system in Europe, which is considered as the largest scale case study. The Met district heating is a second generation system fed by CHP plants, which is supplied by temperature that reach 160s. The analysis is focused on a portion of 60 substations, and the goal is to propose a methodology that allows to find the optimal improvement for modification of pipes, booster pumps, and thermal substations. The decision parameters of the analysis are therefore the diameters of some pipes, the size of some substations, and the addition of booster pumps at specific location. The goal is therefore to find the CAPEX and OPEX cost optimal for various scenarios that allows to respect some constraints, which are the load matching, the maximum fluid velocity, and the maximum absolute pressure. So in order to find the best operations, an evolutionary multi-asset optimization algorithm is associated with a simulator of the district heating network, taking into account the nonlinearity in the network thermofluidodynamics. In the figure, one of the main results represent the multiple optimal solutions which are obtained by the optimizer for different CAPEX and OPEX values. The colors of the point represents the supply temperature which are reached with a specific value of CAPEX and OPEX. So results show that it's possible to reach not negligible supply temperature reduction, and in particular they provide a bunch of possible solutions to the district heating operation, giving them a larger latitude in the decision, also considering uncertainties and unexpected constraints. Now we'll see the approach adopted for the large scale district heating. The Turin system supplies 8,000 buildings at 120 Celsius degrees with CHP plants. It is characterized by a main network of large pipes that we can see in bold and 182 distribution network connecting the main network to the buildings. And some of them are depicted in the figure, and here we can see a zoom of one of them. So in this more complex case, a cascade approach has been used, and in order are considered the district heating to shape the thermal peaks, an analysis on thermal substation, both as is and with modifications, on the network as is and with modification, and an analysis for storage installation. As concerns the substation, for all the big buildings, a basic model has been considered, which includes thermal substation and a fictitious heat exchanger representing like the sum of all the heating devices of the building. The substation characteristics are estimated using the substation data of temperature and mass flow rate and estimated by a proper data analysis approach. So, a model for each thermal substation is adopted to estimate the relation among supply temperature, heat flux, and mass flow rate. This allows estimating a 3D curve like this, which allows to find, given the maximum mass flow and the thermal flux required to the building, which is the minimum supply temperature that can be used for a specific thermal substation. The minimum supply temperature is estimated for about 400 substations in cold winter operation. The figure shows the minimum supply temperature in the descending order for the analyzed substation, and the maximum value achieved is 104 for the most disadvantaged substation. And this means that the system can be, as is, can be supplied at 104 Celsius degrees. And it is also possible to see that less than 20% of the substation require temperature which are larger than 90 Celsius degrees. This means that it is possible to reach a supply temperature reduction of 15 Celsius degrees as is without any investment cost in a typical cold winter day. Here we can see which is the investment required, and the graph represents the supply temperature which can be reached for different specific investment costs. The investment is per equivalent substation, so it must be multiplied for all the substations in the network. So if considering a retrofitting analysis, it is possible to see that with an investment of €1 per equivalent substation, it is possible to make all the substations suitable to operate with a supply temperature of 90 Celsius degrees instead of 120 Celsius degrees. Now let's see if the pipelines are suitable to operate with such supply temperature, since the supply temperature reduction increases the mass flow rate. So this is done using an optimizer to find the maximum mass flow rate supplied to the building and therefore to minimize the supply temperature. So the problem is formulated through a mixed integer quadratic programming and is constrained by maximum and minimum pressure and velocities. The increase of mass flow rate that can be sustained by the system, by the network in a cold winter day is plus 47%. So if considering the mass flow rate increase that is required by thermal substation characterized by different value of supply temperature, an increase of 47% it means a reduction of supply temperature of 100 Celsius degrees. So it means that as is, the system can be supplied, actually the network can be supplied with temperature which are 20 Celsius degrees lower than the current network temperature. Since the congestion in a pipe is located in a pipe connecting the thermal substation, the thermal plant to the city center, how it is possible to achieve the supply temperature that is minus 30 Celsius degrees also in the network. There are two possible solutions. The first is to adopt the twin pipelines, and the second is to use distributed generation, so exploitation of heat pumps, waste heat, and renewable energy sources. And in particular, this will be something that is probably more closer to what will happen in the future with the inclusion of thermal prosumer in district heating networks. Another option for reducing the supply temperature consists in the use of the storages, and this analysis consists in testing different types of storages, sensible, latent, and thermochemical, for reducing the supply temperature in the system for about 400 buildings. In particular, it has been considered that while reducing the supply temperature, the additional mass flow rate required is supplied using the storage. Results show that with sensible storage, it is possible to achieve very low investment costs, but not negligible volumes, while thermochemical energy storages allows to obtain very small volumes, but with larger investment cost. Payback times are in all the cases comparable with the lifetime of district heating. So, in conclusion, potential of supply temperature reduction in existing large-scale district heating is not negligible. This opens to the possibility to feed district heating using renewable energy sources as well as waste heat and heat pumps, and in particular the adoption of proper tools as those presented in the analysis. Preliminary analysis and suitable technologies are suitable in order to perform modification, ensuring high cost-benefit investments. So thank you very much to the audience for the attention, and thank you to IEA District Heating and Cooling that founded the project.